Hey there, chemistry students. This is Ms. Ruark. This is podcast 6.2, where we're talking about how to convert from one thing to another using stoichiometry. Okay, you've had a little taste of this, but let's talk about it some more. So we know that the balanced chemical equation for producing water below says that 2 moles of hydrogen with 1 mole of oxygen can make 2 moles of water. We can't say that the coefficient in front tells us the number of grams. We can't say that 2 grams of water or 2 grams of hydrogen and 1 gram of oxygen makes 2 grams of water. It doesn't work that way. It's not telling us the mass, it's telling us the number of moles that we can get from this equation. And with moles, then we can find the mass that we're looking for. Okay, so remember the reaction describes moles. Okay, well, many stoichiometry problems are going to follow this pattern where we're going to go from grams of one thing to moles of another thing, or grams of one thing to moles of that thing, and then change from moles of one to moles of another, and then we can go back to grams. Okay, now there are some other things that we can have in here, and you'll see this again, but go ahead and write this down on your paper because you're supposed to be copying this little pattern down anyways. Okay, we can go from grams to moles. We know we can also go from volume, which would be liters, of one thing to moles. All right, we can also do particles. Okay, particles, which would be atoms, molecules, or formula units. Right. Let me fix this. I'm going to take away volume. I'm just going to put liters there. That way it's just all kind of the same. Okay, so we can go from liters of X to moles. We can go from particles of X to moles. Or we can go from grams of X to moles. To go from X to Y, or A to B, or 1 to 2, or whatever it is, from carbon dioxide to water, we have to go from moles to moles. And this here is where we use our mole ratio. Okay, don't forget that that mole ratio is a very important part, and it has to be right here going from one thing to another. Okay, and then from moles here we can go to grams. Okay, guess what? We can also go back to liters, right? And we can also go to particles. Okay, now don't forget that the liters, oops, I was going to write liters again. All right, the liters here are going to be only if something is at STP. And remember that at STP, it stands for 1 atmosphere and 0 degrees Celsius. And we know that at STP, that 1 mole of anything is equal to 22.4 liters. Okay, I'm bringing this back up because we're going to use it again. All right, well, let's do some practice. So let's get into example number 1. For this reaction that we've just seen, what is the path that we should take for the following? So all we're doing is setting up the work. We don't actually have to solve for it. So given we have 2 moles of water, we want to calculate grams of water. Okay, so we set up 2 moles of H2O, and we want to go to grams of H2O. Well, to go from moles of one thing to grams of that same thing, we just use our molar mass. So 1 mole of H2O, and this is nothing new, you guys know how to do this, and 18.02 grams of H2O. And if we do that, we would be left with grams of H2O. All right, all we're doing is setting up the work. Okay, so moles of H2O, how many moles are required for 36 grams of H2O? Well, here we're going to start with 36 grams, not H2O. I'm still writing it. It's just H2. Sorry, guys. Okay, so we have 36 grams of hydrogen gas, and we want to know how many moles of oxygen gas. Well, to compare one to the other, we have to go to moles. And whenever in doubt, go to moles, right? So how do we get to moles? Well, we put grams of H2 on bottom, and we put moles of H2 on top. Number with moles is always 1 in a fraction with grams and moles, and then this would be 2.02 because there's 2 hydrogens. All right, grams of hydrogen cancel, but we want moles to go away, so we're going to put moles of H2 on bottom, and we're going to go to moles of O2. Look, this is a mole ratio. That we go to the balanced chemical equation, and we pull in our coefficients. So we would have a 1 and a 2, moles of hydrogen cancel, and we're left with moles of oxygen. Okay, that's how you'd set it up. All right, what about grams of H2O produced from 6 grams of oxygen? That just disappeared. Do you see that? All right, so we've got 6 grams of oxygen, and we want to know grams of H2O. Well, to go from grams of something to grams of something else, we have to have moles. So grams of O2 on bottom, moles of O2 on top. It's the same steps every time, it's just different numbers, right? 1 mole of O2 is equal to 32.00 grams of O2. The grams cancel. Now to go from moles of O2, we put moles of O2 on bottom. We want that to cancel. And we're going to put moles of H2O on top because that's what we're looking for now. Okay, what's my mole ratio? Well, it's going to be a 2 to 1 because there's 2 in front of the H2O and 1 in front of the O2. But we're not done. We want to keep going, right? We want to get rid of moles of H2O and we want grams of H2O. Okay, so 1 mole is equal to 18.02 grams. Moles cancel, and now we just solve. Okay, so all we're doing is setting up the math. We're not actually doing it yet. Here we go. Let's go ahead and start solving. So example 2 says how many moles of H2O can be made using 0.5 moles of ammonia. Okay, so we're looking for moles of H2O. We're using 0.5 moles of ammonia. So 0.5 moles of ammonia. We set this up, fraction, the bottom of the next fraction, we put moles of ammonia because we want that to go away. Okay, what are we putting on top? Well, we're going to put moles of H2O because that's what we're looking for. All right, numbers that go here would be our mole ratios. So that's going to be a 4 to 6. 4 NH3 to 6 H2O. Moles of NH3 cancel. I'm left with moles of H2O. Okay, the math, when we plug it into the calculator, gives us 0.75, but we only have one significant figure, so we need to make sure this is 0.8 moles of H2O. All right, letter B. Let's keep going. All right, letter B, what mass of NH3? So we're looking for the grams of NH3 is needed to make 1.5 moles of nitrogen monoxide. So we're starting with 1.5 moles of nitrogen monoxide. We're looking for grams of NH3. And I'm just setting this up here because sometimes people don't see where they're starting and where they're going. So if you set it up this way, this is what I have, and this is what I'm looking for. It might make it a little bit easier for you to weed out all the other stuff. Okay, so we've got 1.5 moles of nitrogen monoxide. We've got to go from moles of nitrogen monoxide to grams of ammonia. So we're going to put moles of nitrogen monoxide on bottom, but I can't go from moles of one thing to grams of another. I can do moles of one thing to moles of another. Okay, mole ratio, 4 in front of the NH3, and there's a 4 in front of the NO. Okay, moles of NO cancel. And now we got to go to grams of NH3. So we put moles of NH3 here on bottom because we want that to cancel. And we put grams of NH3 on top. Okay, well 1 mole is equal to 17.04 grams of NH3. And now you do the math. So 1.5 times 4 divided by 4 times 17.04 gives us 25.56 grams of NH3. But we want two significant figures. So this becomes 26 grams of NH3. And remember, if I'm going too fast, feel free to pause it, rewind it, watch again. Okay, for letter C. How many grams of NO, so we're looking for grams of NO, can be made from 120 grams of NH3? So we've got 120 grams of ammonia, and we're looking for grams of nitrogen monoxide. All right, so we start with 120 grams of NH3. Multiply by a fraction. On the bottom of that fraction we put grams of NH3, and we're going to go to moles of NH3 because whenever we're in doubt we go to moles. All right, so 1 mole is equal to 17.04 grams of ammonia. Now we can go from moles of NH3 to moles of NO, so we're going to put mole of NH3 here, mole of NO here. This is our mole ratio, so we come up to the problem. We see that there's a 4 and a 4, so we put a 4 and a 4. Makes it easy because they cancel and become 1, right? Yeah. All right, and then we've got to go from moles of NO to grams of NO. So 1 mole of NO is equal to 30.01 grams of NO. And now we do the math. So we plug all this into our calculator. All right, and the calculator gives us 211.338, and there's a lot more numbers after it, but I'm going to stop there. Grams of NO. How many significant figures? I need 2. Oops, that was a 1. So that would be 210 grams of nitrogen monoxide. Okay, You notice it's the same steps every time. It really is. You just got to figure out where you're at and where you got to go. Okay, so example number 3. Here we have the balanced chemical equation, and it says what mass of oxygen gas will react with 400 grams of this C4H10. All right, so we have 400 grams of C4H10, and we're looking for grams of O2. So it's the same thing, right? We're going to go from 400 grams of C4H10. We're going to multiply by a fraction. We want grams of C4H10 to go on bottom, moles of C4H10 to go on top. We know that 1 mole of this is equal to the molar mass, and when we add all that up together, it's 58.14. Grams of this cancel. We've got moles, but we don't want to stop there. We want to keep going. So we're going to put moles of C4H10 on bottom and moles of O2 on top. Okay, this is where my mole ratio comes from. 13 is in front of O2 and 2 is in front of C4H10. All right, but we want grams, so we're going to keep going, right? 1 mole of O2 is equal to 32.00 grams of O2. Okay, and now because our units can't match up with what we want, we can stop and do our math. And the calculator gives us 1431.028, blah, 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 blah. We don't want all that. We want one significant figure, so it becomes 1,000 grams of oxygen gas is what's produced, or is what we need when we react 400 grams of C4H10. All right, letter B. What volume? So we're looking for volume of carbon dioxide is formed. Now that means that we can use this number here or this number here. Now, because it would be I just go back to the original problem. I take what they had in the original problem and use it. We're going to go from 400 grams of C4H10, and we're looking for volume, liters of carbon dioxide. All right, so we've got to set it up again. 400 grams of C4H10. Okay, we want grams of C4H10 to go away, so we put that on bottom. We're going to switch to moles because whenever in doubt, go to moles. All right, we know that 1 mole of this substance is 58.14 grams. Grams of C4H10 cancel. We've got to go from moles of one thing to moles of another. So we're going to use our mole ratio here. Ooh, that was ugly. Let's see if I can erase that. Okay, there we go. All right, so let's try that again. Moles of C4H10, and we want moles of CO2 because that's how we can change from one to the other. All right, mole ratio, C4H10 is a 2 and CO2 has an 8. So we put those in front of those. All right, but we want liters. So let's keep going. We know that 1 mole of any gas, especially CO2, would be equal to 22.4 liters. All right, and now we've got the unit we want, and we can just solve the problem. So when we solve this, it's going to give us 616.44, and I believe there's more numbers after it, but we don't care about those numbers because we have enough. We just need to have one significant figure, so 600 liters of carbon dioxide gas. Okay, so we're doing the same thing over and over again. We really are. Okay, example 4. This one you're starting with moles of hydrochloric acid and you're looking for grams of aluminum hydroxide. And on example 5, you're starting with 1.00 kilograms of calcium chlorate and going to mass or grams of oxygen gas. Okay, I'm going to leave those two with you. I think I've given you plenty of examples. I don't care if it's right. What I want to see is that you've actually attempted to do 4 and 5. So when you come into class tomorrow, make sure that you have 4 and 5 attempted because that's what I'm looking for. Okay, and we will go through them in class so that you'll have them and you'll know how to do them. Other than that, I will see you then.